Muscarella,
and we did our project on motor control. The idea behind this project was to control a wide variety of motors using a feedback system. The feedback system would be a motion detector that would send a high output back to the Arduino based when it was sensed obstruction. The RPM then would be calculated using a little formula determined from the slits on the wheel itself. From this RPM calculation, we were able to adjust the RPM by varying values, and then we wanted to send it back to the user to verify. The step motor is purely controlled with mathematics, and then the DC motor is purely controlled with the feedback system. For the step motor, in our specifications, we were able to achieve 0.01 RPM to about 15 RPM, but we can increase this if we increase the voltage to get about 25 RPM. However, the DC motor goes from 8,000 to 20,000 RPM, and we're able to increase this too if we had a better motion detector. It's basically a little hindered with a capacitor that slows it down. In the end, we wanted to get at least 5% accuracy on both these RPM values. And because the Arduino can't handle 64 bits, we weren't able to really push the DC motor past its 25,000 RPM. And now with the schematic, Heinen Muscarella.
Our system runs off of a positive rail of 5 volts and a negative rail of ground, which are both supplied by our Arduino. We utilize an external digital to analog converter and control it with a SPI interface. The SPI clock, data line, and chip select are all controlled on port B of the Arduino. Our step motor system uses an H bridge control, and it connects on pins 7 through 4 of port D of our Arduino. It sends current to electromagnets or inductors in order to move to adjacent pole locations. Our stepper motor has approximately 4,000 pole locations in a single rotation, and it runs off of the 5-volt rail supplied by the Arduino. Our DC motor is controlled with the output of our digital to analog converter and an NMOS transistor. The output of our digital to analog converter connects directly to the gate of our transistor, determining the current that flows from drain to source. Our DC motor hooks up to an external power supply of 2 volts, and the negative terminal of our DC motor connects to the drain of our NMOS. The source of an NMOS connects to ground. We utilized an external power supply because the Arduino cannot supply enough current to actually run our DC motor. Both of our sensors will send a square wave signal, and it's based on infrared light. It has an infrared light generator and an infrared light sensor. There are 20 evenly spaced slits on disc that are placed on each of our rotors. As the rotor spins, we get a square wave generated, a high voltage from sensed infrared light, and absence of light gives us 0 volts. We have capacitors that run in parallel of our signal path and connect to ground, and this is to make sure that we hold those high voltage values and get an accurate read, although it does slow down the sensing of our motor. This is rather is not directly applicable as it is now, but for future work, we could put it into an RC car or airplane to sense rotation of a wheel or propeller, or we could also use it for energy generation. That could be in a wind turbine or a regular induction or synchronous generator, because there's a peak RPM where you can get max output for your input.
Alright, so demonstration, do we have any volunteers?
We utilize putty, so we can enter our desired RPM for whichever motor you want. So you can go and type in.
Yeah, don't,
Yeah, Gerret will give you
only hit
instructions.
the numbers. Yeah, select the motor you want to use. So it's step motor or DC motor. One per step. Alright, so the first value you're going to enter is your tens place, and then it's the ones, and then the tenths, and then the hundreds. So you have 15 max. Or you can do like 12. You just hit the numbers. It's all.
So it's like if you want 12, you just press 1, 2, 0, 0, because it'll put a
Oh,
decimal.
okay. Okay.
Tell us what you're typing.
Okay, I'll go ahead and do the 12 then. Oh, I see the 0 now.
And then it's going to output the RPM. 15. There we go. It can be a little fuzzy sometimes because the calculation actually stops the step motor from moving because the step motor needs to have signals constantly being sent to it.
So is that why it's fluctuating through the
Yeah,
12,
exactly.
11?
If you look, you can actually sometimes see a little delay.
Yeah.
Do we want to do the DC motor too?
Okay. So you just hit the reset button because we thought that was really simple.
It's hard to implement like a.
So you want the DC motor?
Yeah.
So do the DC motor. And then you're gonna, this is your 10 thousandths place, and then it's thousandths, and then you go.
Hey Josh, do you have a number?
42. Like, how high can it go?
8,000 to 25,000.
21,000, because it's 42,000.
We're gonna, this thing's a little out of control. Yeah. And then you might have to give it a little kickstart. There we
Let's
go.
go on the other
Oh
one.
wow.
And then so it's going to display the average value that it reads.
Oh nice.
And how many, like, how long is the averaging period?
I think it's 4,000 slits
Okay.
or slots, yeah.
So it's
4,000.
2,000 rotation.
Oh, this is really good. You're within
Yeah. Yeah, it's within, that was within 5%.
yeah, easily.
But yeah, it's a little fluctuating because
It's
the
actually-
motor vibrates and our motion
That's
sensor.
well within 1%.
Oh yeah, we wanted 21,000.
Yeah.
I was thinking 20,000.
Yeah, that's good.
That's like the biggest error on there is like 1.5%.
Yeah.
So you're able to reset it just by.
Hitting the reset
Yeah,
button.
and then it's gonna go really fast. And then you can.
Because there's no
Choose
like
your motor.
UART interrupt to like hit a key and have it stop
And
running.
now we can go over the code. So basically, we had to use interrupts, and we didn't actually use these time delays. We used them at the start, but then we figured that our own software delays would be more accurate. We used SPI for the DAC and UART for the user input, and then these are some motor functions, and then we initialize external interrupts. That's actually how the motion detectors send the signal back to the Arduino, and then we have one 16-bit timer that runs. And so here's the main code. We set up all of the output ports for the step motor, and this is for the DAC. And then these ports here are just to make sure we get good signal reads, and we want to initialize the step motor basically, so we put a 1-bit here to get it to start spinning. And then we call our functions, and then this is basically the main loop that happens. We have the step motor run, and it does this action 510 times, and that gives us roughly a single revolution. And then if you selected motor 2, the DC motor runs. So this is just the initialization for the DAC, and then so our motor setup, this is all the UART code basically, and so if you choose a different motor, we have a different RPM value that it gets set to, and then once you enter in all your values, we create this desired RPM, which is a huge multiplication factor of everything. And then for motor 1, this is the magic number that we had that gave us the value for the step motor, which isn't controlled at all with the feedback system. It's just controlled from this master equation. And then motor 2 is, purely feedback system, so we initialize the DAC at 2,000, but we should probably increase that, so we shouldn't have to give it a kickstart anymore. And so the step motor, which we have to increment across all the poles, and then each of these software delays depends on the value of X, which we find from up here. Other than that, the DC motor is just this function, transmitting to the DAC the voltage value. And so this is initializing the interrupts, and we only wanted one interrupt to run when you selected one motor, so this is the interrupt setting. For the initialization, we have it overflow at 4 seconds, or, well, I guess this is like 4.0 something seconds. We're off a little bit. And we have, for the interrupt state, we clear all the interrupts, and then once we get 20 slots, which is 1 revolution, we do the RPM calculation, and then we just print it back to the user. And that's all we did with the step motor. And then with the DC motor though, we have, when it reads 200 slots, because if we read like only 20 slots, we noticed that the feedback system would be too strong. And so we had to increase it. And this basically, if you get your RPM value and we store it into like a mega RPM, which if it was 64 bits, we could probably get more accurate results. And when the DC count reaches 200, basically when it goes into this phase 200 times, we calculate the actual RPM, which is the RPM stored divided by 200. And then we print it out and we reset the counts. And then based on the RPM that we read, we compare it with the desired RPM from up here, and if the RPM we read is less than, we increment the DAC, so we increase the voltage, and then vice versa, and then we reset the count. That's basically what it does. And then our timer overflow just increments the count, but if it's motor 2, then if the count equals 1, so if it doesn't read anything, we put the beat DAC to 2,000. But this should probably be higher, so it actually, we don't have to give it a kickstart anymore. But yeah, that's the whole code.
Does anyone have questions?
Did you consider any sensors other than infrared?
I was looking at like a Hall effect sensor, but it seemed like it would be more of a hassle because we'd have to get some sort of magnetic source, and then we'd have to mount it onto the rotor, and the infrared sensor seemed like the most efficient way to go.
Okay.
So you mentioned earlier that higher resolution encoder would have helped you. You talk about that for a second?
The encoder that we used was when you basically, when the RPM gets too high, this sensor can't read the values, and so with the capacitor, it would only get up to maybe half of the value and drop down, and then we wouldn't actually get a full volt. So our motion sensor just it's very well. The setup itself is very like wobbly. It doesn't give us exact results.
Okay. Thank you.